In this presentation, I am going to explain previous GATE questions and answers for the year 2025, and the topic covered is power electronics. Now let us see the first question. That is, we'll see that this is a 225 GATE question and carries 1 marks. First question is, the input voltage VT and the current IT of a converter are given by, this is the converter, that is given as Vt equal to 300 sin omega t, and the current It equal to, it's not purely sinusoidal, that contains third harmonics and fifth harmonic apart from the fundamental, or It equal to 10 sin omega t minus pi by 6 plus 2 sin 3 omega t plus pi by 6 plus sin 5 omega t plus pi by 2. This is the fundamental component, this is the third harmonic component, and this is the fifth harmonic component, where omega equal to 2 pi into 50 radians per second. The question is that the input power factor of the converter is close. What is the power factor at the input side? That is the question. And the answers are given: A equal to 0.845, B equal to 0.867, C equal to 0.887, and D equal to unity. Therefore, coming to the solution here, the voltage is given as 300 sin omega t, and the current, it is a non-sinusoidal current, contains fundamental, third harmonic, and fifth harmonic. It sin omega t minus pi by 6 plus or 10 sin omega t minus pi by 6 It plus 2 sin omega t plus pi by 6 plus sin 5 omega t plus pi by 2. This is the current at the input side. Now the question is that what is the power factor at the input side? To find out the power factor at the input side, one method is that you can find out what is the fundamental real power supplied by the source. And then we'll be calculating what is the apparent power, and the ratio of the fundamental real power to the apparent power, or P1 by S, that is the power factor at the input side. In order to calculate the fundamental real power at the input side, P1, it is equal to the RMS value of the supply voltage, that is 300 divided by root 2, into the RMS value of the fundamental current, that is 10 divided by root 2, into cosine of the angle between fundamental voltage and fundamental current, which is equal to pi by 6, or into cos pi by 6. It is equal to Vi cos phi, but this is equal to fundamental current RMS value, and this is the RMS value of the voltage, and the phase angle between the fundamental current and voltage, that is cosine of that one, cos pi by 6. That is the fundamental real power. That much real power is being supplied from the source, fundamental real power, which is equal to 1299 volts. Second stage, we have to find out what is the apparent power that is supplied from the, of course, the source side. Therefore, to find out the apparent power, we have to calculate what is the RMS value of the current. It contains fundamental, third harmonic, and fifth harmonic. What is the total RMS value of the current at the source side? In order to calculate that one, we have to square root of RMS value of this fundamental, that is 10 divided by root 2 whole square, plus RMS value of this one, third harmonic, 2 by root 2 whole square, plus RMS value of the fifth harmonic, 1 by root 2 whole square. Therefore, under square root, we'll get 7.245 amperes. Therefore, this is the RMS value, total RMS value of the source current at the input side, and this is the fundamental real power. And once you get, then you have to calculate what is the apparent power. What is the apparent power at the source side, which is equal to the RMS value of the voltage, which is equal to 300 divided by root 2 into the RMS value of the source current, which is equal to 7.245 amperes. And the product is equal to 1536.89 volt amperes. Therefore, this is the apparent power at the source side, and this is the fundamental real power at the source side. The ratio of P1 by S, that is the input power factor at the source side, which is equal to 1299 divided by 1536.89, which is equal to 0.845. That is the power factor at the source side is equal to 0.845, and that is given as the answer is A. Therefore, the answer is option A. Now coming to the second problem of the 2025 GATE question, that also carries 1 mark. Second problem is, in the circuit with the ideal devices, the power MOSFET is operated with a duty cycle of 0.4 in a switching cycle with I equal to, current equal to 10 amperes, and the voltage is equal to here 15 volts, and the power delivered by the current source is given by, what is the power delivered by the current source. This is the, I mean, what is the power delivered by the current source in watts? That is to be rounded to nearest integer. This is a question which carries 1 mark. Now coming to this is a circuit that is given here, and equal we are substituting these values of current as well as the voltage here that is given here. The voltage, sorry, this is the current that is equal to 10 amperes, and the voltage here equal to 15 volts, and this is the MOSFET, and this is the diode. Or this we can consider as a circuit topology can be similar to the boost converter. If you see already, we know that this is the boost converter, and boost converter, what we are being this will be, or these two things, no, the inductor plus voltage source that supplies a constant current, that part is this one in the case of supplying a constant current of here 10 amperes, and the switch is given as this is the switch. Of course the diode is here, I mean diode is connected, and this one, no, this, I mean, voltage source as such, that is considered as the equivalent to a, I mean, capacitor and the load. Now this is being replaced by a, I mean, a battery or DC source. Therefore this is nothing but it is similar to the circuit topology of the boost converter. Now coming to that one, for a boost converter, the relation for output, average output voltage and the input voltage, V0 by Vs, average output voltage divided by the input voltage equal to 1 by 1 minus D, where D is called the duty cycle, that is given as 0.4. And the other relation is that output current divided by input current, average output, that is I0 divided by Is, which is equal to 1 minus D. 1 minus D. This is also another relation. I0 by ID equal to 1 minus D, and V0 by Vd equal to 1 by 1 minus D. Or from this equation we can get output current I0 equal to Is into 1 minus D. Or D is already given as 0.4, and Is is already, we know it is 10 amperes. For 10 into 1 minus 0.4 or 6 amperes. Therefore the output current, that is the current at the I0, that is output current is being calculated as 6 amperes, and the output voltage is given as already 15 volts. Therefore the power, that is, what is the question is that, I mean, what is the power delivered to by the current source to the, I mean, to this side or to the load as such, or here it is being taken as a equivalent circuit is taken as a battery, or that power delivered is given by, that is given by P0 output power is given by the V0, that is output power voltage equal to 15 volts into this current is calculated as 6 amperes, or it is equal to 90 watts. Therefore the answer is in 90 watts. Now coming to the third question, that is in 2025 gate question, that also carries 1 mark. Third question is that an ideal sinusoidal voltage source, that is Vt equal to 230 root 2 sine 2 pi into 50 t, that is sine omega t, like that one, feeds an ideal inductor. Therefore that feeds an ideal inductor through an ideal SCR, and there is an ideal SCR, and the firing angle is of the SCR is taken as alpha is given as 0 degree, and that is, and the inductance values, that is the inductance value is given as 100 millihenry. And the question is that the peak of the inductor current in the ampere is close to, what is that peak of the inductor current here? Answer is, and the options are A equal to 20.71, B equal to 0, C equal to 10.35, D equal to 7.32, that much amperes. Now let us see the circuit. For applying this alpha equal to 0, this can be equivalent, it can be replaced as, can be considered as, I am telling, that is equal to pure diode, like it can consider, because alpha equal to 0. And the inductance value is also given as, of course, it is equal to 100 millihenry. And this is the voltage source, which is equal to 230 root 2 into sine 2 pi into 50. So that is the voltage source. Now question is that, what is the inductor current, peak value of the inductor current? Now coming to the inductor current plot, if you see looking to that one, this is the source voltage, and of course this is the, I mean, load voltage as such. And if you see the corresponding, we will be deriving the equation here. And the inductor current, if you see that one, inductor current is like this one. It will be coming, it is equal inductor current. I mean, this one is that. And the corresponding, to derive that equation, you have to apply the Kirchhoff's voltage law to this loop as such. Then here we will be getting, of course, here, or you can get, I mean, KVL, rather than KVL, we can see that one. Of course, the current through the inductor, as you know that one, current through the inductor is given by the VL equal to L di by dt as such. Therefore, here, I mean, current through the inductor can be written as Vm by L into integral sine omega t d omega t, or Vm by omega L into cos omega t plus a constant A. Or now at omega t equal to 0, the current equal to 0. Therefore, substituting that one, we will be getting A equal to the constant A equal to Vm divided by omega L. Therefore, the current equation, that is the current through the inductor, can be equated as Vm divided by omega L, substituting for A, 1 minus cos omega t. Therefore, this is the equation for this current through the inductor that is plotted here. This is the current inductor plot, and that reaches the maximum value. You can say that one here, if the peak value of the inductor current equal to, that is, if it is, this is equal to minus 1. If cos omega t equal to minus 1, we can say that it is equal to 1 minus minus 1 to a 2 omega. That is happens here. That is at this instant we can say that that is 0 to pi radians. We can say that at the input of pi here we can get it is equal to cos omega t equal to minus 1, or that current equal to 2 Vm by omega L, 2 Vm by omega L. This is the peak value of the inductor current, and that can be calculated as 2 into Vm equal to 230 into root 2 divided by omega equal to 2 pi into 50 into the inductance value equal to 100 millihenry. Therefore, 100 into 10 raised to minus 3, which is equal to 20.71 amperes. For this peak value of the current, it can be calculated as 20.71 amperes, or the answer is option A. For that is the answer. Now let us see the fourth question. That is 2025 gate question. It's a 1 mark. The fourth one, adding 1 mark. And the question is that in the following circuit, the average voltage V0 is given by, that is, this is the circuit as such. The 3-phase input is the, this is a control rectifier is the, of course, this is a resistance, inductance, and a DC source is the, this is the load as such. Therefore, this is the voltage. The average voltage is given by 400 into 1 plus cos alpha divided by 3 into that. This is the average voltage available across the load, and where alpha is the firing angle of this converter, and if the power dissipated in the resistor is 64 watts, that is, the power dissipated in this resistor is equal to 64 watts, then the closest value, what should be the value of the firing angle? What should be the value of the firing angle if you are the power dissipated by the resistor is equal to 64 watts? That's the question. Answers are A equal to 35.9, of course, the firing angle degree, B equal to 46.4 degree, C equal to 41.4 degree, and D equal to 0 degree. That's the firing angle of this converter. So this is the question, and this is a circuit diagram. 3-phase input is the, this is a control rectifier, and this is the RLE load, resistance, inductance, and a battery. So that is the, now for the power dissipated in the resistor, that is the power dissipated in the resistor equal to 64 watts, or that is nothing but the output current square, I naught square into the resistance value is equal to 1. For I naught square into 1, or the current through the load is given by square root of 64, which is equal to 8 amperes. That's the first step. Then after that one, the average output voltage, that is current through this one, is equal to 8 amperes, and the average voltage here, if you see that one, the one thing is that average voltage of inductor equal to always 0. If you see the switching circuit in one, the average voltage, volt second balance to be satisfied. Therefore, the average voltage across the inductor or one switching period should be equal to 0. Therefore, if you apply this Kirchhoff's voltage law to the loop, what is the voltage here? That is equal to the drop across this resistance, that plus this battery voltage, or the average voltage is equal by the drop across the resistor I0R into the voltage E. Now, because the average voltage across the inductor equal to 0. Now, substituting that one, V0 is given in the problem as 400 into 1 plus cos alpha divided by 3, which is equal to I0 calculated 8 amperes, 8 into resistance equal to 1 ohm, plus the source, the battery voltage equal to 500. Now, this is equal to, if you substitute this one, and if you find out the cos alpha from this equation, cos alpha equal to 0.81, or alpha will become equal to 35.9 degrees, or the answer is 35.9 degrees. The answer is option A. This also carries 1 mark. Next problem, fifth problem, that is 2025 gate question, that carries 2 marks. The fifth problem is the 3-phase modulating voltages VAT, VBT, and VCT used in a sinusoidal PWM in a voltage source inverter VSI are, that is VAT equal to 0.8 sin omega t, VBT equal to 0.8 sin omega t minus 2 pi by 3, and VCT equal to 0.8 sin omega t plus 2 pi by 3. Therefore, where omega equal to 2 pi into 50, that frequency is 40 it is not 50, 40, 2 pi into 40 radians per second is the fundamental frequency, and the modulating waveforms are compared with a 10 kilohertz triangular signal whose magnitude varies from +1 to -1, and the voltage source inverter has a DC link voltage of 600 volts and feeds to a star connected motor load as such, and the per phase fundamental RMS motor voltage in volts is closest to, that is per phase voltage closest to, that is a three phase load is considered here, per phase voltage is closest to, question answer is A equal to 169.71 volts, B equal to 300 volts, C equal to 424.26 volts, and D equal to 212.13 volts. Now coming to the problem here, for of course here this is the three phase inverter, voltage source inverter in DC link voltage, that is given as, it is given as 600 volts, and there are three legs are, each leg there are two switches, the feedback diodes are there, therefore this is a star connected equivalent motor equivalent. And here in the sinusoidal PWM signal is used to control the switches, in which these are the modulating signals, phase A, phase B and phase C, and that is compared with the triangular signal, and of course based on that one the switching of this, different switches are taken place. And here coming to that amplitude modulation index is nothing but it is the ratio of the peak value of the triangular signal to the peak value of this modulating signal, and that is given by, that is point here, peak value here, it is equal to peak value, it is the ratio of the peak value of the modulating signal to the peak value of the triangular signal. The amplitude modulation is the ratio of the peak value of the modulating signal to the maximum value of the triangular signal, and which is equal to, peak value is given by 0.8. For 0.8 divided by peak value of the triangular signal is equal to +1. For 0.8 divided by 1, 0.8. That is the MA, amplitude modulation index for this one is equal to 0.8. And the maximum value of the fundamental input voltage, maximum value of the fundamental input after if you in the sinusoidal PWM, maximum value of the fundamental line voltage, maximum value is given by MA into √3. What is the, of course, this voltage, source voltage, whatever this one, that divided by 2. That is MA into √3 Vs by 2 is the maximum value of the line voltage. Maximum value of the line, or the RMS value of the line voltage can be calculated as, it is equal to, for the RMS value of the fundamental line voltage, this is the fundamental, of course, maximum value of the fundamental line voltage is given by MA into √3 Vs divided by 2, and the RMS value of the fundamental line voltage, that is, it is equal to RMS value divided by √2, or MA into √3 Vs divided by 2 √2. Therefore, the question is that what is the per phase fundamental RMS value? We have to find out per phase value. This is the line voltage, RMS value of the line voltage, and to find out the per phase, the per phase value divided by √3. We have to do the divide by √3. Therefore, first we are calculating what is the RMS value of the fundamental line voltage, which is equal to 0.8 into, that's the MA equal to 0.8 into √3 into the DC bus voltage equal to 600 divided by 2 into √2, or which is equal to 293.9338. that much volt is the RMS value of the fundamental line voltage. That is this between phase A and phase B, or phase B and C, or phase A and C. Maximum value of the fundamental line voltage is calculated as 293.93. The question is that what is the maximum value, RMS value of the, no, this is the RMS value of the, this is the RMS value of the fundamental, and the maximum value is this one, and the RMS value of the fundamental, phase voltage is actually not line voltage, it is equal to RMS value of the fundamental phase voltage. Now coming to the question, that is, what is the per phase fundamental RMS voltage? Therefore, here RMS value of the fundamental per phase voltage can be calculated as, what is the RMS value of the fundamental line voltage, that divided by √3. Therefore, here 293.938 divided by √3, which is equal to 169.71 volts. Therefore, the answer is option A. Now let us see the sixth question, that is in 2025 gate question, that also carry 2 marks. The steady state capacitor current of a conventional DC to DC buck converter work in continuous conduction mode is shown in the switching cycle, that is shown here. And if the input voltage is 30 volts, the value of the inductor used in millihenry is, that is round off to the 1 decimal point. Now this is a DC to DC buck converter. Standard circuit diagram is shown here. Buck converter. This is the switch at the input side, and this is the feedback diodes. LC filter is the low pass filter is there, and this is the load is there. Therefore, this is a buck converter topology as such. And here the capacitor coming across the load resistor, and the current through the capacitor is shown here. That is shown as that's here. The question is that what should be the value of the inductor, that is in millihenry. Now coming to that one, if you see the current through the inductor, if you see that one, this is the current, sorry, this is the current through the capacitor, as this one capacitor. We can see that one, here this is the same is shown here. This is the capacitor current, and here current through the inductor is given by the load current plus the capacitor current. The current through the inductor is summation of the load current and the capacitor current. Now, if you are assuming a constant load current, that is added with this capacitor current. Therefore, this is the, the current through the inductor. This is the current through the inductor is given by, it is a summation of the capacitor current as well as the load current. Therefore, this is the inductor current, which is the summation of the load current plus the capacitor current. So, this is the capacitor current. Now, coming to the, in buck converter, you know that from this one, it's very clear that the ripple in current, inductor current, that is, this is the ripple in inductor current is same as delta IL is same as delta IC, because we are assuming a constant load current here. The change in capacitor current is same as the change in inductor current. Of course, here this is the change in inductor current, and that is same as the change in capacitor current. For delta IC equal to delta IL, which is equal to, that is in the problem, it's very clear, it is equal to minus 0.1 to the plus 0.1. Therefore, it is equal to 0.2 ampere is the delta IC, which is same as delta IL. And the switching frequency, from looking from this one, switching frequency can be written as, this is equal to 50 microseconds, or the 1 by 50 microsecond, or which is equal to 20 kilohertz. Therefore, the switching frequency equal to 20 kilohertz for this, buck converter. And the duty ratio can be calculated. Duty ratio means this is the on period as such, and from this is the off period. From the looking from this one, it's clear that it is equal to the on period. This is equal to up to this 30 microseconds, and the total time period equal to 50 microseconds. Therefore, 30 by 50, 30 microsecond divided by 50 microsecond, which is equal to 0.6. Therefore, the duty cycle or D or duty ratio is given by T on by Ts, which is equal to 0.6. Now, the basic equation here, we have to find out the ripple current. What is the ripple current as such? We can say that the ripple current equation, if you the basic equation, ripple current and inductor, actually this current is because of the voltage drop across the inductor. When switch is on, we can say that when switch is on, the voltage across the inductor is given by whatever the input voltage minus the output voltage. Or we can say that in this case, it is written as, we can say that Vd minus V0, or sometimes Vs minus V0, or whatever this, whatever the voltage difference of this input and output is the voltage across the inductor. Therefore, from that only, since it is positive, the inductor current is, the current is building up, because VL equal to L di by dt, or DL by dt equal to VL by L. Therefore, the voltage across the inductor divided by L is equal to the rate of change of current through the inductor. Therefore, based on that equations, we can derive this delta IL, the ripple current in the inductor, which is equal to D into 1 minus D into Vd divided by the switching frequency Fs into L. Or from this equation, we can find out what is the inductor is given by, take this value D into 1 minus D into the dVd, it is written as input voltage, same thing, input voltage divided by the switching frequency Fs into delta IL. Okay, D we already calculated 0.6, and the input voltage it is equal to 30 volts, that is given, and the switching frequency is equal to 20 kilohertz, and delta IL is same as delta IC, which is equal to 0.2 amperes. Substituting this equation, we'll be getting what is the peak to peak current through the inductor. That is, we can get the inductor current used, the value of the inductor peak to peak current, and then from peak base substituting that 0.2 here, you can find out what is the inductance value required. Inductance value is equal to, which is equal to 1.8 millihenry. The inductance required value is equal to 1 millihenry. And what we have to remember in this problem to equation is that in a buck converter, the corresponding ripple current should be equal to d into 1 minus d Vd divided by Fs into L. And similarly, in order to design the capacitor, the corresponding equations to be remembered is delta Vc equal to d into 1 minus d into Vd divided by 8 Lc Fs square. Therefore, in these type of problem, you please remember these equations. From using this equation, you can design the value of the inductor and value of the capacitor, or that you can design the low pass LC filter. The basic equation delta L. L is designed based on the ripple current and C is designed based on the ripple voltage. Therefore, these are the equations to calculate the value of the inductance as well as the value of the capacitance of the low pass filter. This you can remember. Therefore, this is the the sixth problem in the 2025 gate question, and this carries 2 marks.